Hi, welcome to video R-4, Composite and Inverse Functions. Today we're going to talk about evaluating composite and inverse functions and how to analyze their domain and range. And then we're going to talk about how do we calculate composite and inverse functions given that original function. So the first thing we're going to talk about when we're talking about functions in general is today we really want to focus on what is function notation. So function notation is specifically when you have a letter, parentheses, x or y or any other letter usually, but it's typically x, and then an end parenthesis. So like we have here, f of x, this is a function, f, that is made up of x. And so this function f would be something like x squared plus 1, x plus 3x cubed, or something like that. And so the way we say it is f of x. Now this one is a function g parenthesis y parenthesis. This is a function g. So fxn, by the way, is just a shorthand for function. So this is a function g that's made up of y. So the way that we would say this one would be g of y. And so today we're going to talk about composite functions and inverse functions. So with composite functions, we have kind of a fun little notation. We have a function of a function. And so we have f of g of x. That can also be written like this. So we can say this is f of g of x. And that's how we would say that. So the other way you might see it is this kind of notation where there's that little O in the middle. That O just means that this function g is inside of the function f. So f is also composed of function g is another way you can say that. So let's talk about how do you evaluate composite functions. So something pretty simple like f of 3. What you're going to do is you're going to replace all of those x values that you see with 3. So in this case, we have f of x is equal to 2x plus 3. So f of 3 is going to be 2 times 3 plus 3. And so we would say f of 3 is equal to 2 times 3 is 6 plus 3 is 9. And so you could write this as a coordinate 3, 9, which would also be x, comma, f of x, or y, since usually y is the outputs on the coordinate plane. Now let's say you had something like g of negative 2c. So this would be similar to, I'm going to put a little line in here. So this would be similar to just plugging in negative 2c for anywhere that you see x, similar to what we did for 3 and f of x. So here we have g of negative 2c. I'm going to plug in, so g of x looks to be x squared minus 1. So I'm going to plug in negative 2c squared minus 1. And so we get g of negative 2c. We're going to square that negative 2c. So negative 2 squared is 4. C squared is just c squared minus 1. And that's all we have. So we get 4c squared minus 1. And that's it. Now go ahead, why don't you try f of x plus 3 and meet me back here after you finish that problem. Welcome back. Hopefully you got that f of x plus 3, you had to plug in x plus 3 for that x value. So you got 2 times x plus 3 plus 3. So that gave you 2x plus 6 because that 2 got distributed. And then plus 3 at the end. So 2x plus 9 should be your final composition function solution. So now let's look at g of f of x. So in evaluating this one, we have g of f of x. So similar to what you did before when you're evaluating functions, we have g of f of x. We're actually going to evaluate g at f of x. So what that looks like is we're going to plug in 2x plus 3, aka f of x, into the x spot of g. So now we have, okay, so g of f of x is equal to 2x plus 3 squared minus 1. So now we're just going to simplify and evaluate. we get this is 4x squared plus, the trick is 2x times 3, which is 6x times 2, and that's going to give us 12x, plus 9 minus 1. So our final composition is equal to 4x squared plus 12x plus 8. And that's it. So now let's talk about how do you evaluate a composite function when you have a graph. So let's look at the following compositions. F of g of 3. So when we're looking at our graph, you can see that y equals f of x is this red graph, and then y equals g of x is this blue graph. So we have that f of g of 3. So g of 3, that's going to be, I'm going to go to this x value, 3, and I see I'm right up here at 6. And so I have f of g of 3 is equal to, I guess I didn't have to write that twice there, f of 6, which is equal to, so now you're going to go to the other graph, f of x, the red one, and you're going to look, okay, what happens when I go to this 6x value? I go all the way up. It doesn't look like I have my function there. Now, if the function is not there and the graph doesn't exist at that point, then what do? This would be a DNE, does not exist. I specifically included this example because sometimes that will happen, and it's totally okay. Sometimes a composite function does not exist. A composite or composition of functions does not give you an actual value. Now, let's try this other one. So g of f of 2. So this is equal to g of f of 2 like that. So why don't you go ahead and try these next two problems on your own. So before I let you go, actually, let's make sure we understand that this next example is going to be written like this. So go ahead, pause the video, and meet me back here. We will go over these last two examples. Welcome back. So hopefully you found that f of 2, so we're looking at this red graph here, so f of 2 is going to be equal to that y value 1, and so we have g of 1 is our next evaluation, and then we get that blue graph, when x is 1, g is 2. So g of f of 2 is 2. Now for this last one, you have f of 4. F of 4 is actually equal to, all the way up here to 3. F of 3 we got is equal to 0. So the composition f of 4 is equal to 0. All right, so now let's talk about how do you evaluate composite functions algebraically. So there's two ways that you can do this. Now the first way I kind of have set up for you is you evaluate each of the functions at the respective value. And so it's just you go from the inside out versus the outside in. So the other one is you actually create that composite function and then plug in the value you're looking for. So let me show you both ways. Now we're looking at f of x equal to 2x plus 3, g of x is equal to x squared minus 1, just like before. And we have to evaluate f of g of 3. So we're going to do this, like I said, from the inside out for this first way. So g of 3 is going to be equal to 3 squared minus 1. And so we get g of 3 is equal to 9 minus 1, or 8. Now you're going to plug that 8 value in and you get f of 8. Now f of 8 is going to be something like 2 times 8 plus 3. So f of 8, we see 2 times 8 is equal to 16 plus 3 is 19. So you're working from the inside out. Now this is usually pretty helpful and pretty straightforward when you have these nice little algebraic equations like this, x squared minus 1, 2x plus 3. But when you have kind of more unfamiliar values, or maybe you have a natural exponent or a natural log that you're dealing with, it might be more helpful to do it this other way, where you actually figure out what is the composition look like and then plug in your value. So what this is going to look like, we're going to plug in what is the function g of x. We're going to plug that into f of x. So that's actually going to be x squared, whoops, 2 is on the outside. So 2 times x squared minus 1 plus 3. All right, so then we get this composition is equal to, we're going to distribute that 2. We get 2x squared minus 2 plus 3. And so our final composition looks like the following. 2x squared plus 1. Now, you're going to plug in that 3 value because that's what you wanted in the first place. So f of g of 3. And since you already have the composition, you can just plug this 3 value in. So 2 times 3 squared plus 1, which 2 times 3 squared is 9. So that's 2 times 9 is 18, plus 1 is 19 as well. So as you can see, we got the same answer both ways. Now, there's probably a way that you preferred during both of these examples. However, just keep in mind that sometimes the way of creating this composition is going to be a lot more helpful, perhaps because you're dealing with trig functions and you have various values in gradients, or perhaps you have natural logs or natural exponents that you deal with first. This first way I showed you is pretty easy and pretty straightforward if you have very basic equations here and basic values. Now, let's talk about finding the domain of a composite function. So, similar to what you did before, we're actually going to get what is the composition of these two functions. So, we have to figure out what is f of g of x. That's what it's asking for here, f of g of x. So what I'm going to first start with is I have 1 over, and I'm going to plug in negative 2 over x plus 3. Okay, so what I want to do here is I actually am going to get a common denominator. So I'm going to have 1 over negative 2 over x plus, and I need the common denominator with that 3. So this is going to be 3x over x. Because I had to multiply top and bottom both by x. So then this is equal to 1 over, so that's 3x minus 2 over x. Now, what you can also see this as is this piece right here is the reciprocal of 3x minus 2 over x. And so you can actually do this fun little switcheroo. And so the other way you can see this is 1 divided by that fraction, which is going to give you this same result. So you get f of g of x is equal to, and that x is going to flip to the top, that 3x minus 2 is going to stay on the bottom. Now, as you can see here, this was what flipped because you have 1 over this. In other words, you have the reciprocal of this. So this right here, you have, okay, this is our composition, and now we have to figure out what is the domain. So as you can see, we have a rational function here, so we have to look at what are going to be the horizontal and vertical asymptotes. Well, the vertical ones we don't have to worry about, or sorry, did I say that wrong? The horizontal ones we don't have to worry about because that's the range. The vertical ones, that's what we want to look at. And so that's going to specifically involve when is the denominator equal to 0. So 0 is equal to 3x minus 2. So you're going to add 2 over. So you have 2 is equal to 3x. Oh, so it looks like, bring this over here, 2/3 is equal to x. So the range here, so what this means, this is going to have an asymptote at 2/3. So I'm going to write this in a different color, and that means from negative infinity to 2/3, union 2/3 to positive infinity. That is the domain of this composite function. Now, let's go ahead and try the second example here. I'm going to let you guys try that on your own, see if you can find the domain for that, and then meet me back here in a moment. Welcome back. Hopefully you found that when you created this composition, you didn't really need to change anything else. It was just the square root of 1 minus x minus 2. And if you wanted to, you could square that, but it would have just created a lot more nastiness. So this is really just kind of what you need. So in order to figure out this piece, you want to think about, okay, this can only exist if that radical is greater than or equal to 0. So what's inside that radical is greater than or equal to 0. So I have the square root of 1 minus x, square both sides, you get, okay, so 1 minus x is greater than or equal to 0, subtract 1, oh, we have to multiply by that negative, fun little thing. What happens? That inequality is going to switch. And so in looking at this, x is less than or equal to 1. So what that means is we're going to go from negative infinity all the way to 1. Let's just put a hard bracket, just make sure that we're using the correct bracket. But again, keep in mind, AP would actually not fault you if you had the wrong bracket. But that would be the domain of our composite function. Moving right along, let's talk about a one-to-one function and the horizontal line test. So the one-to-one function, every range has one domain. So I did talk about finding a function is one y value for every x value. Now, something that's one-to-one has every y value has one x value, and there's only one for each. So it's 1 to 1. Now, the idea is that one-to-one functions have inverses. So when you take the inverse, it actually switches the one-to-one. So when you're looking at how can you tell if you have a one-to-one function, you have to do this thing called the horizontal line test. Now, the horizontal line test is exactly what you would think. If a horizontal line passes through the graph only once, then the function is one-to-one. Now, there was a test that we had earlier, which I may have misspoke about, but that test is the vertical line test. And that test specifically tells us if it is a function. So that's what we're finding out with that vertical line test. So let's go ahead and see if we can figure out, are these one-to-one functions? Okay, so this top one, I'm going to take a horizontal line and, oh, well, it looks like it passes through more than once, so nope, that is not a function. Okay, well, what about this one? All right. So it looks like I have a horizontal line, and if I pick this line up, I can kind of drag it. Oops, maybe I can't pick it up. But if I bring that up and down, you see it only will ever hit one spot. Even if I zoom in, it's going to go right on that part right there. That's only ever going to hit one time. So this would be considered, this is a yes. This is a one-to-one function. Okay, so go ahead and why don't you test the last three functions? Meet me back here and we'll go through them. Welcome back. So hopefully you got that this graph right here is one-to-one. So we have one range for every one x, or domain. Now, hopefully you also got that this was not one-to-one. So what you can kind of think about is there were multiple x's that were giving you the same y. And so if you look at this, that's going to be typical of trig functions, right? Because if we have pi over 2, I know pi over 2 is 0. It's also 0 for negative pi over 2. So I got the same y value for two separate x's. So it's not one-to-one. Now, for this last one, I have, yep, that is most definitely a one-to-one function. So hopefully you also recognize this should be e to the x, and this is the natural log of x. Okay, so let's look at some key things about inverse function. So when we're talking about one-to-one functions, they have inverses. And there are 4 key things we want to remember. First is that the x and y, when we find an inverse, are going to switch. The second is that in that switch, you can obviously see that it's going to reflect over y equals x, that line y equals x. The domain of one is the range of the other. I'm going to go into a little bit more detail about that. And then lastly, if you have the composition of the function's inverse, it's going to equal that x value. So the function of its inverse is the x value. So f of f inverse of x is equal to the inverse of f of x, which is equal to x. Now, how can you tell that it's an inverse? It has that -1 up top. Don't confuse this with a -1 exponent. That is not super common notation for exponent, -1. We don't see that as often if it's an exponent. Okay, now this specifically -1 is therefore a inverse. So let's talk about calculating this inverse. So I have some steps that I think are really helpful in doing this process. The first is you're going to rewrite this function as a y equals. So we have y equals, so instead of f of x, I have y equals 2x plus 3. Now, the reason why I write it as y equals 2x plus 3 is because my next step is I switch the x and y. So the only reason I make it a y is because then I have less parentheses, less x's, and so I don't get as confused. So it's a lot simpler. So I then am going to switch my x and y, and it's going to become x is equal to 2y plus 3. You literally just switch that x and y around. Now you're going to solve for y. So I'm going to subtract 3 over, and I'm actually going to have 2y. So I'm going to kind of flip the equation. 2y is equal to x minus 3. I'm going to divide this whole thing by 3, and I get y is equal to 1/2 x minus 3/2. Okay, so the next thing that I have to do here is it asks to graph f of x and to graph f inverse. So I'm going to graph f of x. Let's actually graph that in green. We're going to put that in green. All right. Oops. Okay. So f of x is 2x plus 3, so pretty easy linear equation. Go plus 3, and it's got a slope of 2, so over 1 up 2, over 1 up 2. Okay, so we're just going to beautiful linear equation here. Okay, and let's bring that down this way as well. Okay, oops, here we go. All right. So that is our first equation. Now the next one that we're going to look at is what is the inverse equation. So we had y equals 2x plus 3. Now go ahead, why don't you graph that inverse and see if something happens that was noted in these inverse properties. So go ahead, graph f inverse and meet me back here. Welcome back. Now, hopefully you saw that the inverse 1/2 x minus 3/2 is actually going to reflect that green line over that y equals x. So it's going to give us this purple line here. Now, they do intersect. Where do they intersect? They intersect at -3. So if you look here, we have when x is equal to -3, what's going to happen is that we actually get that the inverses are equal to each other, and it looks like they're both equal to -3. So moving right along, Actually, hold on, let me go back up here one second, because is that true? I want to just double check that. So we have 1/2 x minus 3/2 equals 2x plus 3. So where is it that they are actually intersecting each other? So I'm going to subtract 1/2 and I'm subtracting 3. So I get negative 9/2 equals 3/2 x. Oops, 3/2 x. There we are. And so we're going to take out that, yep, does look like x equals negative 3 is that intersection point. Okay, so now let's talk about how do we calculate the inverse of a function when we have domain restrictions. So when we're calculating the inverse of this function, so we have 2x plus 1 over x minus 1, the identity of the domain and range of each. So the first step that we're going to do here is we're actually going to calculate what is the inverse. So we have, whoops, it looks like that's a typo here, f of x. So we have, first thing we're going to do, write it as a y equals. So y equals 2x plus 1 over x minus 1. And we're going to switch that x and y. So I get that, I'm going to do a little switcheroo here. We have x equals 2y plus 1 over y minus 1. Okay, now I'm going to pause this. This is a little tricky one. This is a fun little algebra challenge for you guys. We're going to try to solve for y. So that's the goal here, is we have to solve for y. Okay, so go ahead and solve for y, and I'll meet you back here. Welcome back. Hopefully you found that in solving for y, you got y equals 1 plus x divided by x minus 2. Now, remember that this was our function, f of x, 2x plus 1 over x minus 1. That's the function. This right here, this is f inverse of x. So now remember, the domain of f of x is the range of f inverse of x. So you know what? Let's look at what is going to be the domain of f of x. So the domain, we're going to look at, okay, what is that denominator? What x value can it not be? So I'm going to look at x minus 1. So 0 equals x minus 1. So this can't equal 0. The denominator can never equal 0. So basically, x can't equal 1. And so the domain of f of x is going to be negative infinity to 1 union 1 to positive infinity. Now, this domain right here is the range of f inverse. Now let's look at the domain of f inverse to find the range of f of x. So the domain of f inverse, whoops, wanted my highlighter function here, domain of f inverse. So what we have to look at is, what is x minus 2? So when is the denominator we can't have equal to 0? So 2 cannot be equal to x. And so we have that the domain of f inverse is negative infinity to 2 union 2 to infinity. Now that domain is the range of f of x. The domain of f inverse is the range of f of x. All right, I hope that made sense, and good luck on your homework. See you next video.